Welcome to my YouTube channel, Dhanesh here. So today I am going to discuss about one of the most important algorithms in artificial neural network, deep learning, artificial intelligence, that is back propagation algorithm. See, before getting into this back propagation algorithm, uh, I request you to have some better idea on gradient descent, cost function, and some idea about the differential calculus. Anyway, I will be, revising those algorithms and the maths part as well, along with this back propagation algorithm. So we will start with the back propagation algorithm. See here also I have mentioned you need to learn cost function and gradient descent before this. Cost function, it denotes error. It's the most important term in artificial intelligence and machine learning. Cost function is equal to predicted value minus expected value. You can remember it like this. It is not a complex thing. Cost function is equal to predicted value minus expected value. This is cost function. You may be familiar. Cost function will be denoted by the letter J or sometimes error E, like that. Cost function is error. It gives a predicted value minus the actual value. Actual value, you can call it as target value as well. That is the actual value. This is the cost function. Now, gradient descent, I will give some idea. This is the most fundamental equation for cost function I have given. If you need some more, advanced equation, cost function can be written as, sigma 1 by 2 into y dash minus y the whole square. Here 2 is the calculus factor because when you apply the power rule, derivative of x raised to n is n x raised to n minus 1. To avoid that, we use 1 by 2. Why we are squaring it is the errors can be positive and negative. So when you subtract, you will get positive and negative values. To then they can cancel each other when you add it. To avoid that, you square it. So this is the exact equation for cost function. Even you have modulus you can use. This is the mean square method. There is another method is RMS, root mean square. Anyway, see this equation we will follow in our discussion. So I have given you an idea of cost function. Now gradient descent. It is one of the important algorithms. Gradient descent means I will talk about some idea I will give about gradient descent as well. Gradient descent means it is a repetitive process, or it is an iterative process to find out the minimum of any mathematical function. Gradient descent, we will use it in economics, statistics, artificial intelligence, machine learning, deep learning, everywhere we will use it. So this is used to find out the minimum of any mathematical function. Here in in our algorithm or in deep learning, or in machine learning, this gradient descent is used to find out the minimum of a cost function. To find out the minimum, global minimum of a cost function, we are using this gradient descent. Excuse me. So how do we calculate the minimum? Just some idea I am giving. See, to find out the minimum of a cost function, you can use the calculus approach. There is, a calculus method is there. See, I have a video in the playlist deep learning about gradient descent. You can go through that. There I have, even explained the calculus approach to find out the minimum of a any function. But when the function, if it is very complex, it is very difficult to solve for the value of x, then we will come up with the gradient descent algorithm. In this method, what we do is we will assume a wrong value for the for x, that for that value of x only the function is minimum. We will assume a wrong value for x and we will use this equation after that. This is the equation for gradient descent we are using. It is for if we are considering x, it would be like x of I plus n x. That means x new, the new value of x is equal to xi minus alpha into f dash of, this is the derivative, f dash means the first derivative, dy by dx, f dash of xi. So this is the equation we use. What is alpha here? Alpha is known as the learning rate. You may be familiar with alpha. It is the size of the step. It is the size of the baby step we are using in the gradient descent algorithm. So I told it's an iterative process. It's a step-by-step process. So what is the step length? That is known as alpha. Alpha is known as the step length, and its value ranges between 0 less than alpha less than 1. So the value of alpha is in between 0 and 1. So you can take any value for alpha. So and in between 0 and 1, not any value, in between 0 and 1. So this is known as alpha. It's known as the learning rate. Some people will use eta as well. So both these letters you can use. This is the equation we use. But when we come to, this is for x, see, in our case we are more interested in in neural networks, weight and bias. Am I right? So you will the more we are interested in the weight and bias of the network, right? See, weight and bias, no need to confuse with weight and bias. The simplest equation of a straight line, y is equal to mx plus c. This is the simplest equation. Here m is the slope and c is the y-intercept. This m we call it as the weight of the network. This is the most simplest, this is the simplest equation I can give you. C is the bias of the network. In this way I can easily explain to you. So this is weight and bias. And see, our gradient descent algorithm here we are using to find out the minimum of the cost function. See, our equation we need to how we are minimizing the cost function. See, cost function you need to understand. This is really important. Cost function in our case, it depends on two attributes. One is weight and the next one is bias. So we have to change the equations up. See, previously I have written the equation for x. See, here we have to change the equation for weight and bias. So the equations for weight and bias will be, again we can change it. Instead of x it would be, see, w of I plus 1, w of I plus 1, w of nu will be wi minus alpha into derivative. Our function is the cost function. Cost function I am denoted by E, error function or cost function, or loss function or objective function. All these terms denotes the same, dou E by dou W. We are differentiating error function with respect to weight. This is the equation we use. You understood this. See, error function, E denotes the error function or cost function or objective function. All this denotes the same thing. It denotes error. Now I will how we will get into the, see, the same thing we need to do it for bias as well, because cost function depends on both these. So the new value for bias is equal to the old value of bias minus alpha into dou B by dou W. So in this video I will be concentrating on the weight. So how we will update the weight. I didn't get into the back propagation algorithm till now, so we will be more interested in weight. The same process you can repeat for bias as well. So I am explaining you how do you optimize weight for back propagation algorithm. Same process you can repeat for bias as well. So this is the equation for the bias. So I have covered about the cost function and gradient descent algorithm. So that's pretty enough. Now I will get into the back propagation algorithm. So I told you, as I mentioned, you need to learn the cost function and I have given an idea about the cost function and gradient descent algorithm. So before back propagation algorithm is it is known as, also known as, back propagation of errors. It is, we are back propagating the errors to the neural network. So it is an algorithm for supervised learning of artificial neural networks using gradient descent. It is a supervised machine learning. See, here we have an artificial neural network and an error function. Error function means cost function. This sentence is really important. This is what we do. I have a block diagram for this back propagation algorithm as well. This sentence only, we are showing it in the back propagation block diagram. See, the back propagation algorithm calculate the gradient. Gradient means the partial derivative. The meaning of gradient is slope. It is a slope means dy by dx, the derivative of the function with respect to x. That's all. So the back propagation algorithm calculate the gradient of the error function with respect to neural networks, weights and biases, and find out the global minimum of the cost function. Global minimum of the cost function. Only one cost is needed. Yeah. So this sentence is really important. The back propagation algorithm calculate the gradient of the error function with respect to neural networks, weights and biases, and find out the global minimum of the cost function. See, this is the derivative dou E by dou W and dou B by dou W, and we will calculate the new weight and the updated weight and updated bias. By using that, we will find out the minimum of the cost function, and we will try to minimize the cost function by repeatedly by an iterative process. So you understood this sentence. This sentence is mathematically represented here. I have explained to you. Okay, now we will even gradient descent I have explained you. I have cost function I have explained you, predicted value minus the target value or actual value. All these things I have explained. Gradient descent is used to find out the global minimum of any function. Here we are using gradient descent to find out the minimum of a cost function. No, in a cost function denotes error, and even the most important equation I have given in terms of sigma, predicted minus actual, the whole square. That equation also I have given you. So this is about the introduction to back propagation algorithm. Now we will this gradient descent algorithm. I will give you one block diagram for this gradient descent algorithm. This is what, see, that sentence I told you, that's very important. The same sentence, it is mathematically, sorry, it is represented in this block diagram. Here you have the machine learning model, and we are calculating in the next block we are calculating the error using cost function. So we calculated the error and we are checking it. Error we are calculating by predicted value minus actual value. So we will check whether the error is minimum. Okay, if it is minimum, our model is ready for prediction. If it is not minimum, if the error is not minimum, this all, this is the right side block. It is very important. Update weight and bias of the network using gradient descent algorithm. So if the error is not minimum, we are updating the weight and bias of the network using gradient descent algorithm. And after updating the weight and bias, we calculate the cost function or error again, and we will check it. So we are back propagating the error. That's what we are doing here. So that's why we are calling it as back propagation algorithm. Am I right? So we are back propagating the error. So that's why we are calling it as back propagation of error or back propagation algorithm. So we updated the weight and bias, and again we are calculating the cost function. Then we are checking whether the error is minimum. No. Again, this process. Update weight and bias of the network using gradient descent algorithm. Again, calculating the cost function. Error minimum. No. So sometimes we will do this iteration thousands, 10,000 times to train the model. So this here we are training the model here. It is this is the training process here. It's happening, and finally, if the error is minimum, if it is yes, our model is ready for prediction. So this is the complete representation, the simplest way we can represent this back propagation algorithm in a block diagram. And the equations for gradient descent, it is, I have already told you, these are all the equations for gradient descent. This is the equations for gradient descent algorithm. Equations for GD, gradient descent. Equations for gradient descent algorithm. This is really important. We are going to use it in our this partial derivative. Partial derivative is denoted by delta. You may be familiar. Partial derivatives when come into picture when a function depends on two variables, we will use partial derivative. Our cost function depends on two variables, two or three, multiple variables. That's what I have to tell you. So it depends on two variables. One is the weight and second one is the bias. So we need to get into the partial derivative. That's why we are using dou. Dou stands for partial derivative. If it is if it depends on only one function, we will use the derivative, that is dy by dx. It is d and this is delta. That's the difference. This is delta. This is here we are using delta. Okay, so you got it. What about the equations for gradient descent? Now I am coming to the neural network. See, I will show you the architecture of this neural network. Before getting into this, you need to get some idea about the architecture of the neural network. This is the a simplest architecture. Here we have the input layer. You can give the input. You have the hidden layer. Hidden layer 1, I have maintained two hidden layers in this architecture. Hidden layer 1, hidden layer 2, and the output layer. From there you can take the output. What's happening inside the hidden layer means the computation, the calculation happens inside the hidden layer. And the black arrows represents the weight. Black arrows represents the weight of the network. So all these things you are clear. It's simple, very simple. Input layer, you have the hidden layers. Inside the hidden layer, all the computation, calculation, and activation function. So in the neural network, the one important term come into picture is the activation function. Activations. See, for that I will again see the circles represents the node. Here the circle represents the node. See, each node, the state of a node is denoted by the activation function. The activation function determines whether a node should be activated or not, based on the weighted sum. That is activation function. Activation function, once again, activation function decides whether a node should be activated or not based on the weighted sum of the weights, right? I will explain what is weighted sum. And activation function introduces non-linearity in our neural network. Different activation functions are there. You have sigmoid function. I have a separate video for activation functions in this playlist neural network and deep learning. Please watch it. So activation function different types of activation functions are there. It is sigmoid function, ReLU, hyperbolic tan. The sigmoid function, its value ranges from 0 to 1. So it introduces non-linearity. It can be, any value between 0 and 1. Okay, fine. So we need to get an idea about the activation functions as well. So I will tell you what exactly is happening inside a neural network. For that, I will see inside a neural network, inside a neuron. See, you have biological neuron, right? In trillions of neurons are there in your brain. See, this neuron, that one only, your memory, your imagination, your logical thinking, even your creativity, all these things, your emotions, everything depends on your neurons. How these trillions of neurons works together, that defines all these aspects. But in the same way, an artificial neural network is also different neurons are there. These neurons, that we call it as the artificial neurons, or you can call it as the perceptron. See, this how that perceptron is also the same term we usually use. Perceptron, PRCPTRON. So that we will again getting back to the back propagation algorithm. See, inside an artificial neuron, what exactly happening is only the two processes you need to understand. It will take the first thing, it will take the weighted sum. The artificial neural network will take the weighted sum. For example, if I am taking this first blue node, it will take the sum of the weights coming. See how many arrows are coming towards that blue arrow. Around three weights are coming, right? Three black arrows. See, black arrows represents the weight. Black arrows represents weight only. It represents weight. So inside perceptron or artificial neuron, two processes are happening. One is the weighted sum. After the calculating the weighted sum, it will squash it using the activation function. Squash it using activation function. I am denoting it as sigma. Activation function is denoted by sigma. This is what usually happening inside artificial neural artificial neuron. It's in a single neuron. This is what happening. It will calculate the weighted sum. Very important. Two processes. It's not complex. It's the simplest thing. It will calculate the weighted sum, then squash it using your activation function. Activation function are mathematical functions, sigmoid function, hyperbolic tan, ReLU, all these things are activation functions. Now, once again, I will give more clarity on this. For that, I can tell you the weighted sum, you can write it as, if you have x1, x2, x3 are the inputs, the weighted sum, you can write it as like this. A weighted sum, I am taking the, it is denoted by the letter Z. Then you can write it as a W1 x1. W1 is the weight. Weight represents the black arrow in this architecture. So W1 x1 plus W2 x2 plus W3 x3 plus B into 1. This 1 is the bias. So the value of bias is 1 and B is the weight of the bias. This is really important. The value of bias is 1. So the value of input is x1 and W1 is the weight. Here B is the weight of the bias. Understood. Now this is the weighted sum. Then the output Y will be the sigmoid. Here I am using sigmoid function. See, it is an activation. It's a type of activation function. Different activation functions are there. As I discussed, I am using the sigmoid. So sigmoid of this weighted sum. So those two steps, the mathematical steps, the process steps, I have written in terms of, in the mathematical way. So sigmoid of Z, or you can write it as sigma of Z. So we are squashing the weighted sum by using this sigmoid function. So these are all the two mathematical process in each perceptron, in each artificial neuron happening inside. Again, activation function determines whether a particular node should be activated or not. Even the same thing happening inside your brain. So based on the emotions or the circumstances surrounding you, some group of neurons are activated and you behave accordingly. So the same thing, this activation functions really an important role in our artificial neural network. So you understood what is z, what is y. So this also you understood. See here, I am explaining, I am giving you some more idea about I am calculating the derivative of this sigmoid function. Here I am explaining it because we have to use it in our backward propagation algorithm. See, the algorithm we didn't discuss till now, so we need to use all these aspects. So I am calculating the derivative of this sigmoid function. See, the sigmoid function, I have explained to you what is a sigmoid function. See, the mathematical formula for the sigmoid function is sigma is equal to 1 by 1 plus e raised to minus x. This is the equation for sigmoid function. You see, like this, I will draw this like correctly. 1 by 1 plus e raised to minus x. This is the sigmoid function. I am calculating the derivative of this function because I need to use it in our back propagation calculation. So the derivative of this function is d sigma by dx, because it's x is the variable. So here it is a quotient rule. It is a fraction. I have to use the quotient rule. The quotient rule. It is d by dx of u by v is equal to v into du by dx minus u into dv by dx by v square. This is the quotient rule. You have product rule as well in calculus. So this is the quotient rule we use. So this rule we are going to use it. So by using this rule, you can calculate this sorry you can calculate the derivative of this. So v into du by dx. So I am what is v here? It is 1 plus u by v, 1 plus e raised to minus x into derivative of u. It is a derivative of 1, it is 0, minus u into dv by dx. U is 1, 1 into dv. What is the derivative of v? V is 1 plus e raised to minus x. Its derivative of 1 plus e raised to minus x, 1, it is 0. E raised to minus x, it is e raised to minus x into minus 1, because e raised to x, the derivative of e raised to x is e raised to x. Derivative of log x is 1 by x. You know it. So e raised to minus x, it is see, please learn calculus. That's really important. E raised to minus x, it is e raised to minus x into minus 1 divided by the whole divided by 1 plus e raised to minus x the whole square by v square. That is, this is the one. So this term, it's gone into 0, it's gone. Here it is minus into minus plus, so it would be e raised to minus x divided by 1 plus e raised to minus x the whole square. This is what we got. This I am again rearranging it. So for that, again I am erasing this portion and I will rearrange this answer whatever you got it. So you have this. I am adding and subtracting 1 from here. So you will be getting it as equal to, I am adding 1. The same thing, 1 plus e raised to minus x minus 1. So it's same. 1 and minus 1, it's cancelled. Divided by 1 plus e raised to minus x the whole square. The same thing only I have written. No much difference. You can easily understand this. And then I am splitting it. See, I am splitting it in this way. It is 1 plus e raised to minus x divided by 1 plus e raised to minus x the whole square minus 1 by 1 plus e raised to minus x the whole square. See, this is 1 plus e raised to this, and this square can be cancelled, and this is 1 by 1 plus e raised to minus x. That is our sigmoid function. 1 by 1 plus e raised to minus x is sigmoid. This is 1 by 1 plus e raised to minus x the whole square means 1 square by this. This is minus sigma square. When you take sigma common from this, sigma into 1 minus sigma. This is really important. This equation we are going to use it in the back propagation algorithm. So this is the first part of the back propagation algorithm. Here I didn't discuss much about the back propagation algorithm. I have explained you gradient descent, what is cost function, what are all the steps we are going to do, the block diagram of the back propagation algorithm. All these aspects I covered. So in the next video we are going to finish the back propagation algorithm, the most important algorithm in deep learning, neural network, artificial intelligence. Thanks for watching. Please subscribe.